My greetings to everyone. Today we are continuing our topic regarding mathematical programming. And recall that the course Survey of Optimization is prepared by the Department of Postgraduate Studies of the Vysoké Institute of Cybernetics of the National Academy of Sciences of Ukraine. The course developer is Butenko Sergey, a professor of Texas A&M University. The course advisor is Tetsuk Pyotr Ivanovich, and the course instructor is I, Volovik Elena Ivanova. So the topic of today's lecture is LP programming modeling. And today we will concentrate on a few typical problems which can be formulated and later solved using LP modeling. Among them specifically, we will consider a scheduling problem. Also, we will consider a revised heavenly pouch incorporated problem, which was developed actually in the previous lectures, an inventory problem, a mixing problem, and a transportation problem. Now, let's start from the very beginning. So, let us formulate a scheduling problem as a linear program model. Specifically consider the situation at St. Tatiana Hospital, which uses a 12-hour shift schedule for each nurses, with each nurse working either day shifts or night shifts. Each nurse works 3 consecutive day shifts or 3 consecutive night shifts, and then has 4 days off. The hospital is aiming to design a schedule for day shift nurses that minimizes the total number of nurses employed. The minimum number of nurses required for each day shift during a week is given in the following table. Now, let's consider this table. Okay, so what does this information tell us? Now, first, it says that on Monday, it is required to have at least 16 nurses in a shift. On Tuesday, at least 12 nurses in a shift. On Wednesday, at least 18 nurses in a shift. And so on and so forth with 13, 18, 9, and 7, which will reflect the requirement for nurses on Thursday, Friday, Saturday, and Sunday accordingly. Now, then the information again, which is given to us, says that nurses work 3 consecutive days, meaning that if a nurse starts on Monday, it is here, so then she works 3 consecutive days, meaning Monday, Tuesday, and Wednesday. Then she has 4 days off, meaning that she doesn't work on Thursday, Friday, Saturday, and Sunday. Yeah? In addition, it is required that at least half of the day shift nurses have weekends off. Yeah, meaning that at least half of the day shift nurses shouldn't work on Saturday and Sunday. So, in order to formulate this problem as an LP problem, as always, we start with defining decision variables. In this case, what would be suitable decision variables? At the first glance, one might think that we should define the decision variables as number of nurses working on a specific day, like on Monday, on Tuesday, on Wednesday, and so on and so forth. Then, in this case, we would denote the number of required nurses on a day as x sub I. Well, for example, that would be x sub 1, x sub 2, x sub 3. The number of nurses required for Thursday would be x sub 4, and so on and so forth. Yeah? So in other words, actually, our definition of decision variables would be day focused. But no, let us see what this decision about the variables will lead us to. First of all, what do we need to minimize? We need to minimize the total number of nurses employed, meaning that we would consider all the nurses working on every day, and then we would add them up, and this number needs to be minimized. Yeah, so that would be the objective. But let's think about this. If we sum up all of the variables that reflect the number of nurses working every day, say the number of Monday, yeah, the number of nurses working on Monday will include those nurses that work different shifts. The first shift would be Saturday, Sunday, Monday, yeah, so because they still work on Monday. Then the next shift would be Sunday, Monday, Tuesday, and the third shift would be Monday, Tuesday, Wednesday. So therefore, we would face an overlapping situation, yeah? So therefore, this definition of decision variables leads us to nowhere. So we need to rethink our definition of the decision variables by looking at the input information more insightful. And the suggested definition of the decision variables will look differently, yeah, more reflecting the situation in the hospital, yeah. So depending on the structure of the nurses' shifts, it makes sense to associate the decision variables with the different types of schedules rather than the weekdays. So the suggested definition of the decision variables will look like X sub 1 will reflect the number of nurses the number of nurses which start their shift on Monday. So therefore they would work Monday, Tuesday, Wednesday. Then X sub 2 will reflect the number of nurses which start their working on Tuesday. Therefore their shift would cover Tuesday, Wednesday, and Thursday. X sub 3 will reflect the number of nurses which start their work or start their shift on Wednesday. So therefore, they will work Wednesday, Thursday, Friday, and so on and so forth. The same logic we use for X sub 4, X sub 5, X sub 6, X sub 7. So then we do not have an overlap issue. The total number of nurses will still be found by the summation of all X sub i's here, yeah, and which needs to be minimized. And instead of setting the decision variable as the number of nurses working on a weekday, so therefore instead of defining our variables being day focused, we actually move it to the shift focused approach. So we think in terms of shifts which nurses work. Now, next goal or next step is to state the objective function. So as it was stated in the input information, the objective is to minimize the total number of nurses employed, meaning that we need to minimize the sum of all X sub i's. No, in our case, X sub 1, X sub 2, X sub 3, X sub 4, X sub 5, X sub 6, and X sub 7. Even more interesting, the situation actually stays with the specification of the constraint. To satisfy the requirement constraints regarding the minimum number of nurses working on every day, say on Monday, they come from, no, let's return actually to the definition. So they come from those who start their shift on Monday. So it will be X sub 1. Then those who start their shift on Saturday because they cover Monday too. So it will be X sub 6. Plus those who start their shift on Sunday because it will cover Monday too. So therefore, their constraint will look like X sub 1 plus x sub 6 plus x sub 7. And this summation needs to be at least 16. So that is actually the constraint regarding Monday. With the same logic, we develop the constraints, requirement constraints of the number of nurses working on every day for Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. No, for that, refer to the slide where we defined the decision variables actually to specify actually the indices for those constraints. Interestingly, is that only the first three schedules do not involve working on weekends, and then we will actually explain why it is important. Another constraint which needs to be addressed is that at least half of the nurses have weekends off. And remember what I said, that consider that there are only 3 days when nurses, those who start on those days, actually do not cover the weekends. And those days are Monday, Tuesday, and Wednesday. So therefore, for the number of those who do not work on the weekends, we develop the summation of these 3 variables. And as related to the total number of nurses, which is the sum of all xi's, we need to satisfy the condition of this racial expression being greater than or equal than a half. But this is a racial expression, so we need to convert it to a linear one, and preferably to a standard form. And we do it by performing simple algebraic operations. And specifically, we just use cross multiplication. So this comes here, 2 comes here. Then we'll move all the variables to the left, find the like terms, perform simplification, and actually, finally come up with an inequality in a standard form where we have a 0 here and actually some variables here, which is x sub 1 plus x sub 2 plus x sub 3 minus x sub 4 minus x sub 5 minus x sub 6 minus x sub 7. So therefore, this constraint will reflect the requirement that at least half of the nurses have weekends off. Recall that weekends fall on Saturday and Sunday. So the final model looks like this. Okay, the first line reflects the objective function. So, and remember that we need to minimize the total number of nurses employed. Then these group of constraints, reflects the weekday requirements of nurses working on a specific day of a week. This line reflects the requirement that the requirement that at least a half of the nurses needs to have weekends off. And the last line reflects the requirement for non-negativity of the decision variables. So now let's find a solution. Quickly, I just used the AMPL. Here's the code, launched it, and obtained, and one of the possible solutions is at the bottom of this screen. Here it is. No, yeah, actually, okay, prepared it in a more perceivable way. So what we have received, so the one of the possible optimal solutions is such that the hospital needs to employ at least 31 nurses, and the suggested distribution as for the shifts is Monday, Tuesday, Wednesday, 11 nurses. Tuesday, Wednesday, Thursday shift might have a 0. Wednesday, Thursday, Friday shift is recommended to have 2 nurses. For the Thursday, Friday, Saturday shift, it is recommended to have 3 nurses. For the Friday, Saturday, Sunday shift, it is recommended to have 2 nurses. For the Saturday, Sunday, Monday shift, it is recommended to have 4 nurses. And for the Sunday, Monday, Tuesday shift, it is recommended to have 1 nurse. Now, let's verify the results if they satisfy the inequality constraints. Now, remember that the first constraint about the required number of nurses working on Monday was at least 16. Now, let's check it out. Monday, here's Monday, so 11. So those who start on Monday recommended to have 11 nurses. Then Monday falls on the shift Saturday, Sunday, so there are 4 nurses here. And here is Monday 2, 1, 11 plus 4 plus 1 is 16. 16 is greater than or equal to 16, so the first inequality is satisfied. Now let's consider Tuesday, because there is a 0 here, it might look suspicious. So let's start with this. Tuesday appears here, here, and here. Now let's add them up. 11 plus 0 plus 1, 12. And the stated requirement was at least 12, yeah? Greater than or equal than 12. So therefore, again, the second requirement is satisfied too. So therefore, it is definitely it is a solution, and the optimal one of the optimal solution. Another LP problem will be manufacturer related and specifically maximizing the profit. And again, we will consider the problem, we will actually revise the problem which we stated before and even solved it before regarding Heavenly Pouch Incorporated. Well, but this time we will revise it slightly. So now, for those who do not remember this problem from the previous lectures, I will refresh your memories. So Heavenly Pouch Incorporated produces 2 types of baby carriers, non-reversible and reversible. Each non-reversible carrier sells for $23, requires 2 meters of a solid color fabric, and costs $8 to manufacture. Each reversible carrier sells for $35, requires 2 meters of a printed fabric as well as 2 meters of a solid color fabric, and costs $10 to manufacture. The company has 900 meters of solid color fabrics and 600 meters of printed fabrics available for its new carrier collection. It can spend up to $4,000 on manufacturing the carriers. The demand is such that all reversible carriers made are projected to sell, whereas at most 350 non-reversible carriers can be sold. Heavenly Pouch is interested in formulating a mathematical model that could be used to maximize its profit resulting from manufacturing and selling the new carrier collection. And recall that the original LP formulation model actually would look like this. So here we have the objective to minimize the profit. Also, we have 4 constraints regarding the input information actual requirements. In the last line, we traditionally actually we were at for non-negativity of decision variables. And recall that the X of 1 reflected non-reversible, the number of non-reversible carriers produced, and X of 2 reflected the number of reversible carriers produced. Now let's move it closer to a real-life setting. No, previously we assumed that we couldn't sell more than 350 here, 350 units of non-reversible carriers. But now the management shows some flexibility and considers more than 350 units for a discounted price. Precisely, the first 350 will be sold for $23, and all extra carriers, meaning more than 350, will be sold for a discounted price of $20 a unit. So here is the original constraint. And here is the revised one. So again, we introduce a discounted price for the same type of product. Now let's look how it affects and which changes we need to make to the original model. Now, first look at the definition of the decision variables. As non-reversible carriers, now we can separate into two groups: the one which are sold for the regular price, and the other group will refer to the ones which are sold for the discounted price. So therefore, X sub 1 now will mean the number of non-reversible carriers sold for $23. And we know that the limited number of X sub 1 is no more than 350 units. Now we introduce a new variable and denoted it as X sub 1 prime, which reflects the number of non-reversible carriers sold for a discounted price of $20. And the definition for the number of reversible carriers as X sub 2 actually will remain the same. Then the objective function will be changed into the original function, to the original expression. We add one more term, which is 12 times X sub 1 prime, reflecting the number of units produced and later sold for a discounted price. So why 12? Recall that we are talking about the profit, and the profit is calculated exactly like we did before. Profit. And the profit is calculated as revenues minus costs. Remember that the selling price is 20. The manufacturing cost to produce one unit is 8, so therefore 20 on here. 20 minus 8 is 12. So this is where the coefficient of 12 comes from. Now we need to add the number of units sold at the discounted price to all other variables which contain X sub 1. Yeah, so here we added to this constraint. Now about the coefficient and to this constraint. Yeah, and you see that we added this new variable with the same coefficient as X sub 1 has here and here. So here it is 1, here it is 4. Why? The point is that the resources spent on discounted product and the processes for producing this product are exactly the same. Only the price differs, which is reflected here in the objective function. So that's why here in the objective function. So that's why as the resources to manufacture this product and the processes to manufacture product are exactly the same as required for producing X sub 1. So we use the same coefficients for the newly introduced variable. Then this actually constraint remains the same because we are talking about 350 number of units limitation. This production of these units will start after X sub 1 reaches this value, so therefore X sub 1 prime is not included here. Though we still included into the constraint related to non-negativity of the decision variables. And remember that we speak about maximization. Then, so we here actually I updated the previous code and added what you see, product 1 sold for the discounted price of $20. So and here I just couldn't use the prime symbol, so therefore I denoted it as x3, and after updated all the constraints here and the objective function, and after performing the computations through the solver, and I used the solver minus. So in fact, we obtained exactly the same results as we had in the previous lectures without this discounted product, mostly because x sub 1 is 125, less than 350. So therefore, the value of newly introduced decision variable will stay 0 until x1 will reach the value of 350. But here it hasn't reached it. So therefore, the results remain the same. Now let's consider with this objective function more closely, more insightfully. So what do we actually have? The definition of the objective function is, I would say, somewhat linear. Why? Because it takes, if we graph it on the plane, so therefore the portion of the line before x reaches 350 has this slope. Then when the x crosses 350, after that, the slope changes to 12. Here, the slope is 15 on the interval from 0 to 350. And here, the slope is 12. Actually, it goes lower. With this type of dependence is referred to as piecewise linear dependence, which is a function that is defined on an interval that is partitioned into segments such that over each segment the function is linear. And there are two types of piecewise linear functions. A concave function and convex function. Now, what is the difference? Here, the slope is higher and then it is lower. Here is the opposite. Concave is convex, where here it is low. Notice what this one, and then it increases. The slope increases, so therefore the line is steeper after crossing this point. So generally, and another definition on the concave function is such that this is a function defined on the concave set. The concave set appears to be below the line, and set-wise definition such that the set is concave if for two randomly selected points, if you connect it with the line, so the line will belong to this set too. Now, for example, here, what I take point here and randomly, for example, here, and if I connect it, so this segment will still remain below these lines. Now it will not cross it, so that's why it is concave. The convex actually is just all the same, but instead of the area below the line, we actually use the area above. Again, recall that concave is opposite to convex and vice versa. Concave functions are suitable for maximization LP, so therefore, even though it is somewhat linear, but if we speak about maximization, linear programming model is suitable. And convex functions, convex functions are suitable for minimization. In case we have a convex function, but minimization is required, then the program becomes, model becomes more complicated, additional binary variables needs to be introduced, and the model becomes more complicated in terms of even solution and formulating. So therefore, we will not consider this case. No, and which type of problems will require minimization where LP is still applicable? So no, let's consider another model where minimization is required, that is an inventory model. What can we minimize? If we maximize the profit or revenues, definitely what we want to minimize is the cost, traditionally. One of the possible options. Let's consider the following example, which refers to inventory model. Max Jump LLC plans the monthly trampoline production quantities for the next quarter. The demand during the 4 months is known, so therefore it is a fixed value. For the first month, it is 110 units. For the second month, it is 120 units. For the third month, it is 130 units. And for the fourth month, it is not working. It is 100 units. Presently, MesoJump has an inventory of 20 trampolines. During each month, MesoJump can manufacture up to 100 trampolines with regular time labor of 120 per unit. With overtime labor, MesoJump can manufacture more with overtime labor, MesoJump can manufacture more trampolines costing 150 per unit. Just going a little bit ahead, note that here we have 150, here we have 120, so there is an increase. A per unit inventory cost of $10 per unit is charged at the end of each month. The warehouse can fit up to 25 trampolines, so that is actually one of the constraints. MesoJump's management wants to develop a plan to minimize the total production and inventory costs for the quarter. Traditionally, we start with defining our decision variable. First of all, we have 4 months. So therefore, it makes sense to introduce the horizon, the planning horizon. And we introduce an index set denoted as T, where T equals 1 or 2 or 3 or 4, one of the values, because we spoke about 4 months period. The decision variables. Likewise, we did for producing products which would later sold for a regular price and for a discounted price. So therefore here we separate the number of units made using regular time labor, which is $120 per unit during month T, and number of units made using overtime labor, which is $150 per unit during month T. Here it is X sub T, is Y sub T. But again, remember that it is the same trampoline, the same unit. Then, another thing which makes sense here to introduce is inventory. Why? As we need to compute the total inventory costs, which are included into the total production cost, we need to multiply the ending inventory level for each month by holding cost. So holding cost of $10, which was in the input information. So it makes sense to introduce the variables representing the inventory level. So that's why I sub T appears here. And we will call them inventory variables. So therefore, A sub T denotes the level, the inventory level at the end of month T. Now recall that in the input information, the initial inventory level is 20 units. 20 units is not a variable, it's a value, it's a fixed value. So therefore, let's see how how we will compute actually the inventory level for each consecutive month. For example, for 20, so for I sub 1, it will be initial inventory level plus number of units produced in the first month, including those which are produced with the regular time labor payment and with the overtime labor payment, minus the number of units sold, which is the demand, and again, that is a fixed value which was introduced in the input information. So therefore, general relationship for the inventory level in the tth month can be expressed as I sub t is I sub t minus 1 plus x sub t plus x sub y sub t minus d sub t. So I think actually it is clear. And even though there are some algebraic tricks to get rid of this variable, definitely, but it is recommended to keep it for further transparency and for convenience. And here we may move to formulating of the objective function. Remember that the goal was to minimize the total cost, but the total cost will consist of 3 parts. The first one, regular time production cost, which is $120 per unit of regular time labor, plus the total number of units produced with the regular time labor, which is paid actually on a regular basis of $120. Then overtime production cost, again, which is $150 per unit, in terms of labor, and plus the total number of trampolines produced with overtime labor involvement. And the inventory level at the end of each period, recall that 10 stands for the holding cost. So the final objective function, the final objective function will look like the sum of those 3 parts, 120 times x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus overtime 150 times y sub 1 plus y sub 2 plus y sub 3 plus y sub 4 plus the holding cost, inventory holding cost, I sub 1 plus I sub 2 plus I sub 3 plus I sub 4. Now the constraint. The total number of the trampolines produced with the regular time labor payment is no more than 100 according to the input information for every month. Then the constraint for the inventory level was formulated before. Refer to it again. Then the inventory level cannot exceed 25 units according to the input information. And the last constraint refers to the non-negativity of the decision variables. Remember that the initial inventory level of 20 units is a fixed parameter. It is given. Now, if we write an MPL code and launch it, the results of these computations would be the following. The minimum total cost which the company can reach is $54,100. The recommended volume of production of trampolines is using regular time labor payment is 100 units every month. Recall that we are talking about 4 months period. The recommended number of units produced using overtime labor payment is 0 in the first month, 10 units in the second month, again with overtime labor involvement, 30 units in the third month, and no units in the fourth month. And the recommended inventory level, which is reachable, is 10 units in the first month and 0 units in the 3 consecutive months, which is actually definitely is very good and cost minimizing and quite efficient. So the code in the final solution is not presented in this slide, so therefore that is a do-it-yourself assignment. It is optional, so try to review the AMPL manual more insightfully to develop your own code, debug it, and actually obtain the result. So the result is here. One of the possible results is presented on the slide. Compare yours with what we have here. No, and here again, just I want to say return to the graph here, yeah. So definitely we dealt with the convex function because the initial labor payment was 120 for regular time, and then it increased. It began 150, so the slope of the variable became 150. So therefore, this is a typical convex function. But as we were to minimize it, so therefore LP model is applicable for this situation. Next typical problem, really typical, standard one, is a mixing problem. So we consider another standard problem which can be formulated as a linear program. No, and this is a mixing problem. No, let's consider the situation when a painter whose name is Joe needs to complete a job that requires 50 gallons of brown paint and 50 gallons of gray paint. So this is what he actually needs to achieve. The required shades of brown and gray can be obtained by mixing the primary colors, red, yellow, and blue, in the proportions given in the following table. So, but I want to really fix your attention here. He doesn't really have these colors, these shades. He needs to obtain them out of some other resources. In our case, out of primary colors, which are red, yellow, and blue. So the proportions in the table show that in order to receive the required shade of the brown color paint, he needs to add into it 40% of red paint, 30% of yellow color paint, and 30% of blue color paint. No, and the same is for the gray shade. So he needs 30% of to prepare a mixture which consists of 30% of red color paint, 30% of yellow, and 40% of blue, respectively. But the same shades can be obtained by mixing secondary colors, orange, green, and purple, each of which is based on mixing 2 out of the 3 primary colors in equal proportion. So in order to receive orange, we can, in order to receive red, orange, we can mix red yellow for orange, yellow blue for green, red blue for purple. Yeah. Joe currently has 20 gallons each of red, yellow, and blue. So these are our primary colors. And 10 gallons each of orange, green, and purple paint. So those are our secondary colors. If needed, he can purchase any of the primary color paints for $20 per gallon. However, he would like to save by utilizing the existing paint supplies as much as possible. So formulate the LP, NLP, helping Joe to minimize his costs. Let's consider what we have. So General Joe in his storage or storeroom has different paints. But he doesn't have brown and gray, but he needs to obtain them by mixing different colors. He has primary colors and he has secondary colors. Then he can receive primary colors by mixing secondary ones. Yeah? So therefore we have such a very difficult and complicated process. No, let's start with something what is obvious. No, let's start with the requirement that he needs to obtain 50 gallons of brown and 50 gallons of gray. Altogether, 50 and 50 is 100. So he needs to obtain 100 gallons of paint. What does he have in terms of resources? For resources, he has 20 gallons of each of the primary colors. So it is 1, 2, 3, 20 times 3 is 60. And 10 gallons of each of the secondary colors. 10, 1, 2, 3, 3 times 10 is 90. Is 30. 60 plus 30 is 90, but he needs to obtain 100. No, definitely he will need to purchase something. So therefore, we need to identify actually which color might be purchased. No, will be purchased for sure, because where we will get this then. Yeah. But on the other hand, our goal is to minimize the amount of new paint that we need to purchase in order to complete the job. So essentially, we need to use the existing resources as efficiently as possible. And hopefully, we will only need to purchase 10 gallons of new paint in addition to what we already have. There is no way for us to purchase less than 10, but our objective is to essentially minimize these paints so that we will need to encounter in order to complete the job that we have. Let's start traditionally. First of all, let's summarize all the data we have regarding this problem. So we have source colors, and they are red, yellow, blue, orange, green, purple. 6 colors altogether. Let's use index I for them. But recall that red, yellow, and blue represent primary colors, those colors which can be purchased. And orange, green, and purple represent secondary colors which actually need additional mix. Our target colors are some shades of brown and gray. No shades doesn't matter, so therefore we will simplify just to the words brown and gray. No, there are 2 colors altogether, and we will use the index J for them. So let's specify, and so therefore the decision variables are formulated as gallons of paint of color I used to obtain color J paint. No, and so the Y varies from 1 to 6 and J varies from 1 to 2. And X sub I, gallons of paint I purchased. Why do you have 1, 2, 3? Because there are only 3 primary colors which can be purchased. So now let's consider the availability. What do we have? We have 20 gallons of red, yellow, blue, primary colors, and 10 gallons of orange, green, purple, secondary colors. And the requirement is 50, at least 50 of each required color. So again, as we said before, here 50 is 50, we have 100. If we add up all the available gallons of the paint, we will receive 90. So therefore, definitely, we have some deficit. Yeah. No, let's start. No, let's go on with the object. Okay, object. So our objective is to minimize the costs for Mr. Joe. So 20 cents for the $20 purchase. X sub 1 refers to the red color, then 20 again dollars, so the purchasing price for yellow, and this is for blue. 20 x sub 1 plus 20 x sub 2 plus 20 x sub 3. Now there we have some constraints, so we need to specify the constraints. The total amount of brown and gray paint made must be at least 50 gallons each. So therefore, if we mix up all our both primary and secondary paints all together, we need to obtain at least 50 gallons. Now, in this inequality, in these two indices, 1, 2, 3, 4, 5, 6 stand for the available paints, and 1 stands for brown, yeah, that we need to receive the brown color. No, and similarly, actually, we developed the next inequality constraint for gray paint. So this is what we need to obtain. Now, then the constraints for other constraints, yeah. So the amount of each paint used for mixing must not exceed its availability. Here we have 20 here stands for the availability of the red color plus x sub 1, again, some red paint, which can be obtained by mixing orange, yeah, orange and yellow, yeah, or to be mixture, all these mixtures, yes, in the stated proportion. So this is the same actual stance, availability stance for that is red, yellow, and blue, yeah, for the 3 primary colors. And this is the availability for the secondary colors. Remember that secondary color paints, remember that we have actually 10 gallons of each. Then the proportions. So 3 out of 6 colors used for mixing contain red, and the total amount of red paint, included that coming from orange and purple, actually they mixed, yeah, orange and purple paints used in the brown mix is. So the red in the brown mix, then the orange. Remember that for us to receive red, we need to mix them in the equal proportions. Equal proportions, that a half of one and a half of another one. So that's why we have 0.5 as the coefficient of for the volume of secondary. And here we have secondary paints, 4 and 6 stands for the secondary one, contained in the brown paint. A constraint for the proportion of red color in the brown mix is reflected by this ratio equation. Yeah, so this actually goes at the numerator, and the denominator actually introduces the total number of paints in the brown, of all paints actually in the brown color paint. So, and that is according to the input information, it is 0.4. But of course, the ratio equations are not convenient for us. So let's convert it to a linear one by multiplying the both sides by the denominator, then moving all the variables to the left-hand side, performing typical simplification algebraic operations by finding the like terms. And finally, this equation will be converted into a standard linear equation. 0.4 or 0.6 times x sub 1, 1 minus 0.4 times x sub 2, 1 minus 0.4 times x sub 3, 1 plus 0.1 sub x sub 4 minus 0.4x sub 1, 5 plus 0.1 times x sub 6, 1, and everything being equal to 0. So this is actually a standard linear equation. No, in the same manner, actually, we for yellow and blue colors in the brown mix, again, recall that those are primary colors. After converting the racial expressions, equalities, actually, we come up with the same equalities in a standard linear form. Here they are. So, therefore, the summary, the summary for the gray paint constraint will look like the ones on the screen. Again, the first line will refer to the red color in the gray paint. The second is yellow color in the gray paint. And the last one is blue color in the gray paint. So the final, almost final, because it is too long, so therefore it occupies 2 slides. The final mixing problem LP will look like this. So the first line represents the price for every primary color. It is 20. So we need to minimize it. So we want to minimize actually the purchasing amount. Yeah, so the cost. Then this part represents the proportions of different colors in the required shades of brown and gray. So this is for the brown, this is for the gray. So this one refers to the requirement of the volume of paint needs to be obtained. Remember that at least 50 gallons of each. And the last portion of inequality constraints reflects availability, actually, of the paint. And the last line, actually, refers to the non-negativity constraint of all the decision variables involved. And the final widely used linear programming program, and it was formulated as linear programming problem by famous mathematician Leonid Kantorovich, is a transportation problem. The standard actual formulation of the transportation problem is as follows. A wholesale company specializing in one product has M warehouses denoted as W sub I, where I varies from 1 to M, serving N retail locations denoted as R capital sub J, where J varies from 1 to N. N is the number of retail locations. Transporting one unit of the product from warehouse I to retail location J costs C sub IJ dollars, where I varies from 1 to M and J varies from 1 to M. The company has S sub I units of product available to ship from a warehouse To satisfy the demand, which is at least D sub j units of the product, must be delivered to a retail location J, denoted as R sub j. The task is to formulate an LP model to decide how many units of the product should be shipped from each warehouse to each retail location so that the company's overall transportation costs are minimized. Again, we speak about minimization. In general, transportation problem is formulated using the decision variables defined as the product quantity shipped from a warehouse I to a retail location J. No, definitely all variables must be non-negative. Then the objective is to minimize the total cost of transportation, which involves the transportation from a specific warehouse to a specific retail location, and the summation of the products reflected by the product quantity and the price actually of shipping. Then the constraints which will be involved is such that the number of units shipped out of the warehouse does not exceed S sub I. Here we are actually recall that S sub I is units available on the warehouse. So therefore we cannot deliver more than we have. So therefore this constraint is formulated algebraically as the sum of all xij's by the j index from 1 to m, and it cannot be actually less than available product. And the demand, so the demand needs to be satisfied at every location, so therefore the sum of the shipped products quantity, well, cannot be lower than the required demand, which is D sub j. So the final formulation, LP formulation of the transportation problem is presented on this slide. Okay, so with this, thank you very much for your attention. Traditionally, we meet at 4 o'clock on Thursday. The meeting link will be posted later. Thank you very much for your attention and have a very good time.